Good evening, everyone. Today is the first day of our new lecture series on the lightweight hybrid multi-story design and construction by Professor Tisan Jayasinghe, and also our chairman, Civil Engineering Sectional Committee, Engineer Mangala Silva, has joined. I would like to invite him to do a welcome. Thank you.
Thank you very much, Engineer Banduka. Is Professor Jayasinghe in now? Sir,
Yes,
can you hear me?
Yes, I'm in.
Okay, sir. Actually, thank you very much, sir. Actually, dear participants and dear members, I would like to warmly welcome all of you on behalf of Civil Engineering Sectional Committee for this lecture series of Professor Jayasinghe. Actually, I would say that I don't think that I need to give an introduction about Professor Jayasinghe because he did a lot of lectures. I'm sure most of you are the students of him. Actually, I consider this as a great honor for me to do this welcome speech because he was my research supervisor when I'm doing my BSc in University of Marathon as well as when I'm doing my master's. So I worked with him more than 20 years. And he also, about 2 years ago, he as the chairman of Civil Engineering Section Committee, he did a lot for the betterment of civil engineers. I'm sure he has created thousands of students to this country as well as in other countries. So I believe, and also I want to mention one important thing this time under the guidance of Professor Tishan Jayasinghe and his assistants, Civil Engineering Section Committee of IESL created the stall for the techno this year, and we could won the gold award. So there we exhibit the rammed earth techniques and methods explained to us by Professor Jayasinghe. So we could achieve that gold award. I believe that is after 10 years. So with that statement, I would like to invite Engineer Professor Jayasinghe to do this lecture series. It's over to you, sir. Thank you.
Okay, thank you, Mangala. Now you can see there are many tables and so on. And so what we do is I'll give you a very brief introduction about Eurocodes and why it all happened. If you look at the history, right? If you look at the history of these Eurocodes goes back to Second World War. So after the Second World War, if you look at the history from 1914, there was a war. We call it First World War, and over 500,000 people were killed in that one, 14 to 1980. So Germany was defeated, and again Germany came back as a force, and we had another war. So after the Second World War, the world learned that these wars are not going to help anybody. So the Civil Engineering Sectional Committee, lecture number 1, lecture 1 on 29th November 2020. So I'm numbering all the pages so that we can share the notes later. So after 1945, by 1950, 51, they were actually looking at the possibility of having better cooperation rather than having wars. So with that, there was a peace treaty. And this peace treaty finally led to something called European Union. So in the European Union, you get Germany, France, and then Austria. So there are so many countries. And England also joined them later. Then, so they wanted to, although this started as a peace treaty, then it went on to an economic treaty. And gradually they thought, okay, let's have the construction was one of the main economic activities. So they thought, okay, let's have one standard across Europe. But if you look at Europe, you get Italy. What is Italy is a country subjected to earthquakes. And if you look at Italy, it is a more tropical weather. Whereas Germany, no earthquakes, but it's cold weather. So they thought, okay, if you are going to have one standard that can be used by everybody, then we can't have one standard across all the different climatic conditions. So you get so they thought, okay, let's have one code, and we'll allow nationally determined parameters, nationally determined. That means, they can differ from the generally proposed parameter in the Euro. So with that, we got something called national annexures. And you will find that, as when a code is developed, there can be many parameters. And so basically, Eurocode had its own values, but when it comes to a particular country, you can have preferred values not for all the parameters, but for selected parameters. So Eurocode spells it out, saying that these are the recommended values, but you can use the values given in the national annexure. So if you look at Sri Lanka, historically, we remained as a colony of UK, England. So we also use British standards for quality assurance, quality controlling, and design. So if you look at quality assurance, quality controlling is also based on BS codes. All the testing was based on BS codes. So we were very happy about it. But have you ever thought why BS codes are so applicable to Sri Lanka? So if you look at England has 3 to 4 months of summer. What is the temperature range? Now the temperature can change between 20 degrees to 30 degrees. In Sri Lanka, throughout the year, the temperature can vary between 20 and 34. So you can see if you have a certain standard applicable to England, which is a temperate country, temperate climatic conditions, not cold climatic conditions. So we can actually use those standards pretty well. We can use those standards pretty well in Sri Lanka as well. So if you look at Eurocodes, they have 36 codes altogether. So you can see, if you want to be a very good designer, you should know all these 36 codes. And, when these Eurocodes came into action after 2010, because all the British code standards to cease operational in 2010, a very good initiative was taken by Sri Lanka Standards Institute, and Engineer Mangala Silva also participated as the representative of IESL. And they have already completed few national annexures. So basically, they have looked at the British national annexures very carefully and done only minor changes, and kept most of it without changing because they are actually applicable to Sri Lanka. But so if you are not having a national annexure, you don't have to worry. We can simply use the national annexure of England, because United Kingdom, because those are actually applicable to our country to a great extent, so we don't have to panic or do something. We can simply change over to Eurocodes without worrying very much, because UK national annexures are all already available. So that's how it goes. So if you look at the loading, the approach for loading is one of the key things that we start for a design. To start a design, we must know loading. Not only loading, we must know how to generate critical conditions, critical combinations. If I take an example from British Code, a simple example that most of you are very familiar, Civil Engineering Section Committee, 29th, 11th, 2023. So, Mangala,
Yes,
can you hear me?
Yeah, yes, I can hear you.
Today we have participation exceeding 200. Is that right?
Yes, 211. 211.
Yes. Good. Right. So basically, if you look at a beam, let's take a simple beam. Take a simple beam. So in the British Code, we say, okay, we must have GK. That is the dead load. Then we say, okay, you can have imposed load, QK. And we can have QK in different ways. That means these two have QK, or we can have QK. What is the effect? Effect is we are having a bending moment diagram that goes like this here, and we have a bending moment diagram that goes like this here, or we can have a bending moment diagram that does that, and here also we can have a bending moment diagram that does that. So we can have different diagrams. So to get the most critical combination on a beam, we say, okay, let's go for pattern load. Go for pattern loading. So when you are going for pattern loading, we say we have three spans. You can have 1.4 GK plus 1.6 GK, or else you can have two other patterns where you have 1.4 GK plus 1.6 GK, and this is 1.0 GK, or else we can say this one 1.0 GK, 1.0 GK, and here you get 1.4 GK plus 1.6 GK. So we can have pattern 1, pattern 2, pattern 3, and if you look at the bending moment diagrams, so we'll have a beam having a bending moment diagram like this. That's due to pattern 1. Then due to pattern 2, which is this one, pattern 2 is this one, we can have a bending moment diagram that does this and going that way, or else we can have a third pattern, this pattern 3. You can see the pattern 3, we can have something like this. expanding, right? Giving an envelope. And once we have the envelope, we say, okay, now we have an envelope and we are going to make use of the envelope, not the diagram. Not the diagram. We are going to say, we are going to make use of the envelope. So similarly, corresponding to this, for here also, we will end up with an envelope, right? For here also, we will get an envelope, but for the time being, we will concentrate more on the flexion, right? So now we see, right? Okay, so we have to go for an envelope like this, and what we do is we use the most critical values. For example, we use this value, we use this value, we use this value, and here you can see we are using those two keys. And so that's how we go about in British code. Then let's look at now that is all subjected only to the vertical loads. Then let's look at a structure. So if you have a structure, it can be subjected to vertical loads, it can be subjected to lateral. So to take account of lateral loads, it says, okay, consider case 1, 1.0 GK plus 1.4 W. Case 2 says, look at 1.4 GK plus 1.4 W. So that means we are considering the full window. Case 3 is saying all acting together. W. Case 4, 1.4 GK plus 1.6 GK. But where applicable, consider pattern load. So this is what the British code says. Now let's see what the Eurocode says. Eurocode is slightly different in this approach. So this is what the British code says. Case 1, case 2, case 3, case 4. And for case 4, it says consider pattern loading as well where applicable. Consider pattern loading as well where applicable. Right. So it is it's clear. But now let's look at Europe. Now I'm looking at Europe. So it talks about the dominant effect and other effects. So let's have a quick look at how it goes by sharing the screen. So if you look at the structure, we can have so many different actions and combinations of actions. Due to self-weight, ties and floor coverings, weight of partitions, loads, weight of fixtures, plumbing, weight of fixed furniture. So those are the vertical actions. Those are the permanent actions. Variable actions, weight of furniture, people, wind loads, snow loads, direct actions, thermal effects, differential settlement. Those are variable actions. So when you look at loads, what we do is we multiply the basic loads by appropriate partial factor gamma f, and to get the characteristic loads. When more than one live load or variable action is present, the secondary live load may be reduced by the application of combination factor finder. See table 3.4. And the basic load combination for a typical building becomes, so you can see gamma G for the dead loads, gamma Q for the imposed loads. And this is a primary one. So the secondary one, you get another phi naught factor. So what it means is, I'll stop sharing. What it says is, okay, it's fine. We have the structure. Now we are talking about all types of loading. What it says is, okay, right, you can have GK. What is the factor? 1.35. Instead of 1.4, you have 1.3. Plus QK, dominant. Then you can have 1.5. But when these two are dominant, you can have wind load also dominant. So we have WK. For WK, the factor is 1.5. But you have to consider it as multiplied by 0.5 times. So the combination will be 1.35 GK plus 1.5 QK plus 0.75 W. Whereas in British code, we have 1.4 GK plus 1.2 QK plus 1.2 W. Now you are having this one, but at the same time, you can say WK can come this way, QK can go that way, then you can have 1.35 GK plus 1.5 WK plus 0.7 times 1.5 QK. So you will end up with 1.35 GK plus 1.5 WK plus 1.05 QK. So you can see the combinations. So instead of this one single case in British code, now you are going to get a number of cases. 1.35 DK plus 1.5 UK plus 0.75 WK as one. The other one is 1.35 DK plus 1.5 WK plus 1.05 Q. Instead of this 1.2, 1.2, 1.2, here now we are getting 1.35, 1.5 and 1.6. So this is the main difference in the load patterns that you see with Eurocode and BS. BS codes is very straightforward, but you will see in Eurocode also it's very straightforward. Only thing is there are factors because you can't have wind load and live load all acting together with maximum. You can have either the impulse load acting maximum or wind load acting maximum, but both cannot be maximum at a given time. And in British code, it was taken into account by reducing the partial factor of safety for all up to 1.2. But in Eurocode, we do the same thing in a slightly different, but in a more logical manner. Is that clear, Mangala?
It's clear, sir.
It's clear, right?
Yes,
Very
sir.
clear. Right. Now we look at it in more detail by looking at the note. Now we look at the note. In the chat, we say, see all, please join. Okay, right. Okay.
That's for that study materials, sir.
Yeah, study material. Right. So I'm going to share the screen now. Right. Now you can see GK, QK, QK, and QKI. So you can have number of things combined, but for each one, so you can say sigma, but you have a phi naught factor. So let's see what is this phi naught factor. So it says, now you have to become a little familiar with these reduced factor of safety for dead loads and imposed loads, 1.35 and 1.5. And earth and water, that can generally consider their permanent actions and factored accordingly. Earth and water loads all should be multiplied by 1.35 because they are permanent loads. If they are permanent loads. Now let's look at this one. We are interested in this pi naught factor. Except for storage areas, generally the pi naught factor is positive. But when it comes to snow loads, wind loads, it reduces to 0.5. And when you are looking at temperature effects, you have to use 0.6. Then you look at why you are having some other factors, phi1 and phi2. When you are using the Eurocode, at certain places, you will find it uses phi1 and phi2 factors as well. Whenever you see phi1 and phi2 factors, you must come back to this table and have a look. You must come back to this table and have a look. I can actually share this note with all of you, and I will send it to Engineer Mangal, and he will make some arrangement to share it with all the participants. Is that okay, Mangal?
Sir, I think Engineer Mangala left for now. I am Bandhuka.
Yeah. So I'll send it to Bandhuka. Bandhuka can coordinate it.
Sure, sir. Okay.
Right.
I will share.
Okay. So basically, I will send this note, and traffic area vehicles, traffic area 30 kilonewtons, vehicle to 160 kilonewton. That means 3 tons to 16 ton area vehicles, roofs, snow loads above at high altitudes, and snow loads and wind loads. So there are so many factors, but let's not worry about this phi1 and phi2 for the time being. Whenever we come across those in equations, we'll look at what is meant by phi1 and phi2. But generally, we should know what is meant by phi naught to use Eurocodes. And then it also says unfavorable and favorable factors should be used so as to produce a most onerous condition. Generally, permanent actions from single load source may be multiplied by the unfavorable or favorable factor. For example, all actions originating from the self-weight of the structure may be considered as coming from one source. And there is no requirement to consider different factors on different sources. Exception of these are overall equilibrium is being checked. So let's have a quick look. What is meant by this particular situation? And these are all from EC1. Let's look at this one. In Eurocode, pattern loading is considered to find the worst case possible when checking the structural adequacy. When pattern loads are considered, only the variable load is pattern. For permanent load, either 1.0, 1.35 can be used. One which gives the worst effect can be used. So generally what we do is, when you are checking the pattern loading, in British code we use 1.0 GK here, but in Eurocode we use 1.35 times GK. We don't, because in the British code we use 1.4 when it is fully loaded for GK, 1.0 GK when it is 0. When it is only the die load is only the dead load is available, we use 1.0 GK. But in Eurocode, here you can see we are using 1.35 GK. Minimum load is also 1.35 GK. It doesn't change. So that is one of the variations you can again see with British code and Eurocode. So I will stop sharing so that I can draw and show you. Right. So basically, when you want to design a beam, what we go for pattern loading. So to get the worst case scenario, we use maximum here, minimum here, maximum here. So that is 1.4 GK plus 1.6 GK. But here 1.0 GK. But in Eurocode it says okay, it is It's the same thing you are doing, but this is 1.35 dk plus 1.5 qk. This is also 1.35. It's not 1.0. That's another important change you have to keep in mind when you are generating pattern load. And actually, it's very easy to generate pattern loading um, using a computer because of this particular condition. Because of this particular condition, it's very easy to generate pattern loading using a computer because we are using the same parameter for the dead load. It can be either 1.0 GK throughout, but because you are using 1.35 GK plus 1.5 QK here also you have to use 1.35 GK. So that's how it goes. So we use 1.35 GK, but not 1.0 GK as we have done in British codes. Banduk, is that clear?
Yes, sir. That is clear.
That's clear. So that has to be kept in mind. So this civil engineer sectional committee, page number 7, and the date is 29/11/2023. Then let's look at a little more details. Then I'm going to share the note again. Now we are looking at the combinations. Dead and imposed 1.35, 1.5. Dead and wind 1.35, 1.5. Dead imposed and wind 1.35, 1.5. Dead imposed, but wind should be multiplied by 0.5. So 1.5 multiplied by 0.5 is 0.7. Dead imposed wind, you have another combination where wind is kept full. This imposed is multiplied by 0.7. 0.7 multiplied by 1.5 is 1.05. It's B. 1.5 multiplied by 1.5 multiplied by 0.5 is 0.75. Why it happens is, if you look at the previous table, phi 1 factors, phi naught factors. For wind load is 0.5. For domestic conditions and all the other conditions, it's 0.7. So imposed loads is 0.7, wind loads is 0.5. So you can end up with a table like this. We'll end up with a table like this. And then you have to look at this condition. Now you are looking at the stability or the worst case scenario for a shear wall. So this side you get to get tension, and to get the tension, the self weight has to be minimum. Now you can see in that situation, on the tension side, you get 1.0 GK, and on the wind side, while the wind is 1.5. Whereas, so we are looking at lateral stability. So, and also whether tension can occur and the shear wall can track on this side. So to make sure that happens, we maximize the wind, minimize the weight. So you can have a combination called 1.0 GK plus 1.5 WK. In British code, it used to be 1.0 GK plus 1.4 WK. Here you can see it's 1.5 WK. And then the British code had 1.2 GK plus 1.2 QK plus 1.2 WK. Instead of that, you get 1.35 GK plus 1.05 QK plus 1.5 times WK. And here you can see in British code, we had only one dead imposed wind case, which is 1.2 GK plus 1.2 QK plus 1.2 WK. Whereas in Eurocode, we have two combinations when dead, imposed and wind are acting. So here the imposed load is dominating case. This is the imposed load dominating case. This is the wind load dominating case. So here you can see wind load is 1.5. Here the imposed load is 1.5. So this is dominated by wind imposed load. This is dominated by wind load. Is that clear, Mandu?
Yes, sir. That is clear.
That's clear. Right? Good. So, right. Now let's see what is reinforced, how to design reinforced concrete. And to design reinforced concrete, we have to see how we define the strength. In Eurocode, all strengths are defined in terms of cylinders. Cylinder strength was used by Japanese and British earlier, and cube strength was used by British. So what is the difference? Actual strength is the cube's cylinder strength. Cube strength gives a higher value than the actual strength. Actual strength of concrete is 0.8 times cube strength. So don't think that cube strength is the actual strength. It's not. Cube strength gives a higher value. Then you have to ask the question, why? So what is the reason? What is the reason for cylinder strength to be actual, cube strength to be an overestimate? And we know the size of the cube is 150 by 150. Whereas the height of this is 300. And when you are testing, we place the cube between two thick steel plates. And these two steel plates, what happens when you apply a load this way? You get something called nu times sigma. Nu is the Poisson's ratio. That is the theory that we have learned, I think even in advanced level, as far as I can remember. Anyway, in the university you learn it. So what happens? When the cube tries to break, these places are restrained. So because of that, the cube strength is higher than the actual strength. So this gives the actual strength, this gives a higher strength. So we have to always keep in mind, cylinder strength is not the actual strength. Actual strength is only 80% of the cylinder strength. Is that clear? You have to be very clear about that, right? So cylinder strength is the actual strength, whereas cube strength gives a higher value. So now you can see. Now let's look at. Let's share the note again. So here you can see the strengths. When the FCK means cylinder strength, FCK cube means cube strength, right? So that's the notation used in Eurocode. And so here you can see when you have 20 megapascal cylinder strength, cube strength is 25. So when the cylinder strength is 25, it's 30 for the cube. So we say we have C 25 30 concrete, C 30 37 concrete, C 35 45 concrete, C 40 45 concrete, C 45 55 concrete, or C 50 60 concrete. Now you will ask why I have not included the table beyond 60. So cube strength of 60 is a special value in Eurocode, and it actually allows you to go up to 105 cube strength. But the equations that you use are generally valid up to 60 megapascal, but if you are going to use concrete beyond that point, concrete stronger than 60, then you have to have different parameters for the design equations. You cannot use the normal design equations if you are using anything beyond 60 megapascal. So that's why I have included only up to 60. Why? 60 megapascal cube strength. What is your perception? Is it a strong concrete or a weak concrete? 60 megapascal is a very strong concrete. So if you are going beyond that, you have to keep in mind there can be some adjustments needed for the design equations. So we concentrate up to 60 megapascal in this course because you know there can be minor variations when you go beyond that. Then there are tensile strength values that can be used in pre-stressed concrete. But because in reinforced concrete, we consider that the concrete is cracked. Concrete is cracked. So we don't have to really worry about tensile strengths. But when you are designing for pre-stressed concrete, you need to worry about those. And you can see here, if you look at the stress strain curve, you can see the maximum strain allowed is 0.0035, and by looking at the stress strain curve, we can get more information. And here you can see. Now you can see the full curve. I have reduced the size of the screen slightly.
Yes, we can see it.
Yeah, you can see it. Right. You can see the whole thing. Now this is the stress strain curve for concrete, and you can see FCK is the cylinder strength, and we have to consider 85% of that. Now you might ask why. The reason is we test the concrete in compression, then we use that value in flexion. So because of that reason, the frictional strength of concrete in compression is considered as 0.85 times the cylinder strength. 0.85 times the cylinder strength. And then it says, right, it starts to be a plastic material from a strain of 0.002. And it cannot take a strain more than 0.0035. 0.0035 is a very familiar figure. Even in PS code, we consider that concrete cannot take a strain of more than 0.00. So this is the stress strain curve for concrete. And then if you look at the strength of concrete, we get the flexural strength of concrete as 0.85 FCK. And if you want to know the stress that you can allow in concrete, we have to divide it by a partial factor of safety. And the partial factor of safety that we use is 1.5. Now, can somebody tell me why it's 1.5? It is 1.5 because we are supposed to cure concrete once we place it. But many people do not pay enough attention to cure concrete. So what happens? We can't use 0.85 FCK because we might be overestimating the actual strength of concrete in the structure. So to allow for that, we use a high factor of safety, not because we are making bad concrete, but we don't cure adequately. We don't we do not cure it adequately. Because we are not curing it adequately, there can be variations in the strength. It is not only because we are using different ingredients and make concrete, but curing also comes into play. So curing is very important, and we must cure concrete. In this point, data allows for the long-term effect, the difference between cylinder crushing strength and concrete and bending strength. Value 1.5 is used for partial factor, safety factor for concrete, for the strength of gamma C, and you can see up to C50-60 concrete, we can use 0.0035, but beyond that, it will be less. Then let's look at steel. Eurocode allow steels from 400 megapascal to 600 megapascal tensile yield stress. Yield stress can be 400 to 600. Eurocode specifically says any steel used should be 400 to 600. So that means we can make use of all tow steel. Tow steel had a strength of 460. But these days we use QST bars, quench and self-tempered bars. What we do is, we get the steel bar manufactured as red hot. Then we pour water onto it, making a very hard surface on the surface. And then we allow it to cool down gradually. And when cooling down gradually, the toughness might reduce to a certain extent, but it remains very hard. The interior remains very soft. So when you bend the bar, the chances of the bar breaking is very remote. And also you can get a higher strength by adjusting this heating and cooling process. You can get a higher strength. You can go for 550 steel or even 600 steel. Might be a good idea for Sri Lanka because steel is very expensive in Sri Lanka, so might be a good idea to go for 600 strength. But at the moment we have only 500 strength. So we'll remain at 500, but because steel is manufactured under proper conditions and it doesn't need any curing type situations, we have a smaller factor of safety, 1.15. The factor of safety is 1.15. And the elastic modulus of steel is constant, 200 kilonewtons per meter. So now you can see something very important about steel. What is that? Elastic modulus of all steels is 200 kilonewtons per meter square. But let's look at the elastic modulus of concrete. Elastic modulus of concrete. What do you see? The elastic modulus of concrete increases. Sorry. This is not elastic modulus. This is the average strength. Let's see how it's here. Here, elastic modulus of concrete. Here you can see 27, 29, 30, 31, 33, 34, 35, 36, 37. So elastic modulus of concrete increases as we use higher strength concrete. So what is the advantage of this? This is a huge advantage in tall buildings because by using high strength concrete, we can have a higher elastic modulus. With a higher elastic modulus, we can reduce the deflection in a tall building. So in tall buildings, this has become one of the key reasons for concrete to dominate now. Early days, steel dominated the buildings. Steel was the key material. Now, if you look at today, you'll see concrete is the main material. Why? Because as we use high strength concrete, elastic modulus increases, which has a huge advantage when you are considering the lateral deformation and lateral response, lateral movement based response of the structure when subjected to earthquakes and wind loads. So there's a huge advantage. So that's why in all the tall buildings that are coming up, like including the 1 kilometer tall Kingdom Tower in Saudi Arabia, Burj Khalifa, all have used concrete because concrete is a wonderful material to control lateral deformation, because as the strength increases, the elastic modulus increases. Whereas in steel, even when you consider the pre-stressing steel, it is high strength steel, the elastic modulus is 200. So those are the important things you can learn about steel and concrete. And then comes how to make concrete durable. And if you look at the history, the Roman emperors who knew about concrete, over 2000 years ago said, we have invented a material that is going to last forever, because they had only concrete. They did not have steel. But today, when you have only concrete, the best shape is arch shape. But today, we don't use arch shape a lot, but we use beams, columns, slabs a lot. So these members are subjected to flexure, whereas arch shape is generally subjected to compression. Because these shapes are subjected to flexure or bending, we need reinforcement. The moment you insert reinforcement, concrete does not become a material that is going to last forever. Why? So that's what we are going to learn now. So I'm going to, I'll stop share. Right. So, yeah. Now we say, we pour concrete. We are always advised you must have a cover. So this is a cover. Generally, in according to British code, we used to have 25 to 40 millimeters of cover. Right. And what happens when you use concrete? That's very important. Because if you are going to learn about concrete, you must know what is meant by concrete. For that, we look at the cement. Cement is some material that we only add water plus gives us a gel. But the gel is very strong. So what do you get in cement? Tricalcium silicate. What is the importance? It's active only for short period, 1 to 14 days. We get dicalcium silicate. It is a very slow reaction. The reaction actually starts after about 2 weeks, but it can continue. Then we get tricalcium aluminate. Very rapid reaction. And then it is from 1 hour to 24 hours. But the problem is we can't have too much tricalcium aluminate because it can lead to destruction of concrete after a while. So this has to be less than 10%. This can be anything, but generally it's about 65 to 70%. And in the modern concretes, this is only 5 to 10%. Modern cement. And then you can get tetracalcium aluminoferrites, and that is an impurity that you cannot prevent when you manufacture cement. So what is the reaction? Reaction is tricalcium silicate. Dicalcium silicate also gives the same reaction, but a very low rate. You get tricalcium silicate gel plus calcium hydroxide. Now, this calcium hydroxide is a very important ingredient because when you use concrete, what is the minimum water cement ratio needed? 0.2. What are we using? We use 0.5. So what will happen? All this extra water. Extra water will be evaporated. Then what do you get? Porous concrete. So then what happens when you continue to cure? We continue to generate calcium hydroxide, and all that calcium hydroxide will start filling up these voids. So it's very important that we cure concrete because we are going to fill up all these extra voids by calcium hydroxide. So that's why, when water flows on calcium on concrete, you get some whitish color substance coming out, and that is calcium hydroxide, washed away. So we create calcium hydroxide, those will fill up those tiny pores. And calcium hydroxide, what is the pH? In well cured concrete, the pH can be close to 12 to 13. You cure it well. You don't cure it, it can be less. So, in ferrous, you would have seen, we all know, once ferrous is exposed to the atmosphere, it will form a ferrous oxide layer. What can you say about the stability of this layer? It's not stable at all. That's why we see, unless we paint steel, what happens? Unless we apply a paint coat, what happens? It undergoes corrosion. But so when you have a reinforcing bar outside, it also undergoes corrosion. But we put it inside the concrete. What happens? The moment you put it inside the concrete, it stops its corrosion. Why? When pH is 12 to 13, this ferrous oxide layer is very stable. Like aluminium oxide layer. You have seen these buses, Tata and Ashok Leyland, having aluminium bodies. But aluminium is a much more reactive metal than ferrous. But why can we have a bus body or a cooking saucepan to boil water? Because aluminium oxide is very stable. Inside that you get aluminium, not stable at all. But the moment it is exposed, it will form the aluminium oxide layer. Similarly, this ferrous oxide, ferrous also, the moment it is exposed to the atmosphere, it will form a ferrous oxide layer. And if the oxygen and water is available, it will continue to undergo corrosion, forming oxide more and more. But the moment you insert the reinforcement into the concrete, because concrete is highly alkaline, this ferrous oxide layer is very, very stable. But what happens with time? We have carbon dioxide in the atmosphere. This carbon dioxide will start reacting with calcium carbonate, gradually form a layer. And that is called carbonated concrete. So what is the problem? Carbonated concrete pH can be around 9 to 10. And that means it's not stable. When pH is 9 to 10, it is not stable, but still it will take plenty of time. In a well-cured concrete, for about 25 to 35 years, you might get only 10 millimeters of carbonation. Well cured. But if you don't cure it well, even in 10 years, you might find the carbonation can be 10. So, which means what is the minimum cover that we need? We need a minimum cover of 20 to 25 millimeters if you are expecting to have a reasonable duration without any trouble in a concrete structure. That doesn't mean that the moment it comes here, it is going to corrode and the structure going to collapse. No, it's not. So if you are protecting the structure, oxygen content is low, and the oxygen cannot come into contact with the reinforcement. Water is not available. It's all in dry condition. Even a carbonated structure can last many years, but you're asking for trouble. You're asking for trouble when the carbonation has reached the steel. So you have to take a lot of precautions when you are maintaining. Before that, even if you don't do anything, still concrete will protect the steel. No corrosion. No corrosion. So that's what you have to keep in mind. And so, what is the lesson we can learn from this? Any question on this? Although it's on one page, it's a very important lesson. It has all the information you need to explain why reinforced concrete should be properly cured. Why reinforced concrete should be properly cured. It has all the information that you need to know why reinforced concrete should be properly cured. Manduka, any question you like to ask? Anything?
There's one question, but it is not directly related to this, sir. Wanted to ask, how about what are the recent advances in lightweight but high performance concrete?
That one I will come in a little later, right?
Okay.
Because that's the next thing I'm going to talk, right? Not lightweight, but normal weight, high performance, right?
Okay.
Because lightweight high performance is something different, because lightweight concrete can be made only by using lightweight aggregates. Right? Because either you use lightweight aggregate and get a lesser density like 18, or use normal aggregate and get a density of 25. Right? But high performance concrete is something different. That I can explain. Right? Okay. So if you are using lightweight aggregate, you will get lightweight. But you can't get lightweight concrete by using cement. Right? So how you get lightweight concrete is by going for very high strength aggregates, which are very low in density. Then you will find overall density of concrete as reduced. So whereas if you want high performance concrete, it's something different, because there we are using normal aggregate, but we want high strengths like 80, 90 megapascal. So that's what I'm going to explain now.
Okay, right? And also, and also one question related to this from an engineering student. He has asked, when will start to cure after the concreting? Likewise,
no, actually, you should not allow direct solar radiation onto a concrete once done. Because direct solar radiation can start evaporation. So the thing is, first thing is, make sure the concrete is covered as soon as it's done. But after about 24 hours, you must definitely start curing. Right? If you don't have to do anything within the first 24 hours, because there's plenty of water in the concrete, but what you need is to protect it being exposed to direct solar radiation. Any fresh concrete exposed to direct solar radiation can lead to very high evaporation of water from the finished surface, leading to cracking called plastic settlement cracks and plastic cracks. And those cracks will go up to the reinforcement. And the problem with that is, because these can be more than 0.3 millimeters of crack width, a lot of oxygen and carbon, lot of oxygen and water can penetrate easily into the concrete and start corrosion. So what is bad is exposing a freshly cast concrete to direct sunlight or wind that will lead to high evaporation rate from the surface soil. That must be prevented. But you can start curing after 24 hours. There's no problem with that. Is that clear?
Yeah, that is clear, sir. But in practically, how can we prevent from exposing to direct sunlight in a construction?
That's why, a lot of large concretes, they start the concreting around 6 o'clock in the night, evening. By starting the concreting around 6 o'clock in the evening, you can prevent most of these problems. So in our tropical climatic conditions, large concrete should be done after 6 o'clock. Overnight. That's the way. Because if you do large concrete pours during daytime, you are asking for a lot of unnecessary trouble, especially due to exposure to the direct solar radiation. The reason is direct solar radiation has an energy of 800 watts per square meter. So it's like having a electric heater on the concrete when you expose it. So the ideal is, if you are doing large important concrete, always make sure it's done during the night.
Okay.
Is that clear?
One more question participants have asked. They have asked whether how to use curing compounds or membranes?
Actually, curing compounds are ideal for cold climates. In our warm tropical climates, direct solar radiation, under the direct solar radiation, the chances of these compounds working properly is very remote. So in Sri Lankan conditions, I always prefer water cure because we have a very high tropical, we have a tropical situation where the solar radiation intensities are very high, so the concrete can heat up and sometimes these curing compounds might not work. But water curing will definitely work. Is that clear?
Yeah, clear, sir. Clear, sir.
Yeah. Okay, right. So, because curing compounds are very good when the outside temperatures are low and the solar radiation intensities are low. Then the concrete is kept cool and no chance for evaporation of water. Whereas our conditions are very harsh because water evaporates. The moment the sun comes out, water evaporates. So water curing is the best in Sri Lanka. Right, now I'm going to talk about how to get concretes with higher strength. So that now first we'll see. Let's say we want C2530 concrete. Now what is C2530 concrete? That is cube strength, cylinder strength. This is cube strength. So what is the mix for a 30 megapascal concrete? So what do you get in a mix? Cement, sand, aggregate, water. And on this side you get wet density. You get wet density. Cement, sand, aggregate, water, and wet density. Cement, how much? 30 into 10 plus 50. 350. What is the water content? Whatever the concrete is 200. What is the wet density? 2500. When these numbers are fixed, if sand is X and Y to X ratio is generally between 1.9 from 1.5. Why do we need this lower limit? If you don't have a lower limit, you will find there's a lot of sand in the concrete, but no aggregates. Why do we need this one? Here you will find a lot of aggregates and no sand, no mortar. So this has to vary between this. And we'll assume that we are using this value. So the mix is 350, 200, 2500. So 2500 minus 200 minus 350, 1950. So we can say X plus 1.5 times X is equal to 1950. This X, Y, X, so Y O X is 1.5, so Y is 1.5X. X is 1950 divided by 2.5. And the value is, what is the value, Banduka? 1950 divided by 2.5?
780.
Yeah, 780. Okay, so we get 780 multiplied by 1.5. What is the value?
1170.
1170. Right. So you get 350 cement, 780 sand, 1170 aggregate, 200 water, giving a wet density of 2500. So this is a mix without admixture. But we know these days we like to use admixture. Why? Why we like to use admixture is admixture can help us to reduce water content. How an admixture works? Admixtures can disperse the cement particles well, and when the cement particles are dispersed, they can act as a lubricant. So with a lesser amount of water, you can get a higher work. So let's say now we have decided to go with an admixture. So we use 160. It's all that. At the moment you are using admixture, we know in concrete who is our friend? Cement. Who is our enemy? Water. Now you reduce the enemy. then you can reduce the flint gas. Reduce it to 380. So now we have knocked off 30 here, 40 here, 70 kilograms. So that 70 should come from here. So we might get 805 and whatever the corresponding value here. What is the corresponding value? 2500 minus 320 minus 160 comes to 2020 minus 805. So you get 1250. Is that right? 2500 minus 320 minus 160 minus 805 is equal to 1215. Is that right?
Yeah, 1215.
Yeah. So this is a new mix. Now let's say you have decided, okay, now I'm little concerned about this thermal effects. Like when you add water to cement, what happens? You get a reaction where the temperature rises. When the temperature is more than 70 degrees, we can get this tricalcium aluminate reaction occurring in the reverse direction, and it will lead to tricalcium aluminate in the original form inside concrete. And after a while, this can start expanding again, causing cracks in concrete. So I can show a figure. Right. Now, do you like a concrete designed by you cracking like this, or constructed by you cracking like this? This is a large concrete form. What do you think? Do you like this kind of cracks in a concrete structure?
Not at all.
Yeah, but this is a reality in Sri Lanka. This can happen in Sri Lanka. When you make concrete, you must control the maximum temperature below 70 degrees. If you don't do it, you can get cracks like this.
So according to my knowledge, it has happened in Sri Lanka, no? This is in a photograph taken in Sri Lanka, if my memory is correct.
This is Southern Highway. Southern Highway pile caps. A pile cap in Southern Highway bridges from Kurunduga Atamba to Mathura. This happened in Sri Lanka. Okay?
Not everything.
So the important thing is you must control the temperature below. Delay formation involves controlling the maximum temperature rise to newly placed concrete to be below 70 degrees. This needs careful controlling the cement contained in concrete. The charts developed could be of immense value for structural engineering in this endeavor. So we have prepared some charts which actually tell the full story. So I will come to the chart in a little moment, but before that I will now explain how to deal with this delayed ettringite formation. What is the rule? Higher the amount of concrete, higher the amount of cement, higher the tricalcium aluminate content, higher the tricalcium silicate content. So tricalcium aluminate will give the initial strength, like our ability to remove the formwork within 24 hours is given by tricalcium aluminate, giving a strength of about 10% of the target strength. Now after 24 hours, what happened? Tricalcium aluminate becomes super active and it's acting very fast, generating a lot of heat. So if you want to prevent delayed ettringite formation by keeping the temperature below 70 degrees, what do you have to do? Minimize the cement. And how do you minimize the cement? Let's say we use 260 kilograms of cement and 60 kilograms of fly ash. So this fly ash, and the moment you use 60 kilograms of fly ash, you'll find the density on this side will also come down. Still, we can keep the water at 160. Now, we are not changing any of these parameters. 800, 1200. Why? The wet density has reduced by about 20 kilograms per meter cube because fly ash has a lower density than cement. So now we use 60 kilograms of fly ash of lower density. Now the final wet density also has reduced slightly. But this is not lightweight concrete, this is normal weight concrete. But how much cement available? 260. And fly ash reaction is not going to start immediately. How the fly ash reaction starts? Fly ash is a pozzolanic material, which means fly ash is going to react with the calcium hydroxide that we generate. Plus fly ash will give tricalcium silicate gel. So gel is given. What happens? Concrete will now go in a different path. Now you can say, if you look at the textbook, what the textbook says, if you are expecting the final 28 days strength as 1, these 28 days, in 7 days, we get 2/3 of strength. We get 2/3 of strength, right? These is what the textbooks say. Now what happens today? And the textbook curve was done when tricalcium silicate was limited to 50%, dicalcium silicate was 25%. Now today, what do you get? You get about 65 to 70% of this, 60 to 65% of this, only 5 to 10% of this. What happens? Now the reaction goes in a different curve. It reaches 7 days strength 28 days very fast, but it does not increase the strength very much. It goes in a curve like this. So that's why we say, if you can cure concrete for 7 days these days, it is sufficient. You don't have to cure it for 1 month. But the moment you add fly ash, what happens? When you add fly ash, because we are less cement now, it will go more in a curve like this. But the advantage here is it will continue to gain strength. It will continue to gain strength by this reaction is going to happen beyond 28 days. So it will continue to gain strength. So what is better? Using fly ash or without using fly ash? Using fly ash is good, and the percentage can be 10% to 25%. The percentage can be 10% to 25%. So today we can buy cements blended with fly ash from leading manufacturers, and most of the cements have some amount of fly ash. On the other hand, we can buy Portland cement and mix it at the site. And if you look at Portland cement, we pay 40 rupees per kilogram. And fly ash, you will spend only about 10 to 15 rupees per kilogram. So you can reduce the cost of concrete by adding fly ash at site, where you pay the same amount for Portland cement. You don't buy blended cements, you buy Portland cement and mix fly ash, then you can reduce the cost of concrete. On the other hand, you are not concerned about the cost, you are concerned about the ease. How easily you can make concrete. You might not buy, you will buy a blended cement with 15% fly ash. Then automatically you are adding fly ash to the concrete and reducing the rate of reaction. And with a lesser rate of reaction, you have lesser chance of forming delayed ettringite formation. Is that clear, Mangala? Is that clear?
Yes, sir. Yes, it's very clear.
We look into all this problem in Sri Lanka, and we thought, okay, let's give a tool to the design engineers when they are doing the design. So the tool is this. So here you can see, you can read this paper, you can download it by typing MTR Jayasinghe DEF under the Google search. You can directly download the paper. And anyway, I will send a copy to Engineer Bandukha. Okay, let's look at this chart. What it says is, if you are using 275 kilograms of cement, whatever the thickness of section, the temperature will remain less than 70 degrees. So this is a peak temperature. This on this side section thickness. We are using no fly ash, and the placing temperature is 30. So you can see, whatever the thickness, the maximum, even 3 meter thickness, the temperature remains less than 70 degrees when you use 275 cement. But the moment you go up to 300 cement, what happens? Temperature exceeds 70, so anything beyond 1.5, 1.2 meters is in danger of cracking, forming DF. So how can we prevent this situation? Okay, so what we do is, we use 275 cement, but we like to have about 350 cement. So what are we going to do with the remaining cement? We, instead of using cement, we use fly ash. So we need a cement mix of 350 cement, but we don't call it cement now, we call it cementatious material. So we'll have a cementatious material of 350, where only cement is only 275, and fly ash is 75. And what can you ensure? You can ensure that concrete will never exceed 70 degrees. On the other hand, let's say we have to use 300 kilograms of cement, and we are using 75 kilograms of fly ash, giving about 25% ratio, coming closer to 25% ratio. But you can see now the temperature is going to be about 73 degrees, 74 degrees. The pore is very large. Temperature is 73, 74. What are you going to do? You are going to reduce the placing temperature. Placing temperature is 32. What we can do is we can reduce the placing temperature. How are we going to do that? We are going to wet the aggregates the day before, so that water will evaporate by taking all the energy in aggregates. And we'll use 60% water and 40% flaky ice when you are mixing. So we do everything that we start cool. When you start cool, you might find that the placing temperature can be dropped to about 26 degrees. Because we have used we have removed all the energy in the aggregates. So they are all cool, no energy in it. And we are using flaky ice, 40%. Then you get a cool concrete, and the placing temperature can be 26. So placing temperature is 26. If the placing temperature is 26, what is the maximum temperature? It will be below 70, because without cooling at 32 degree placing temperature is going to be around 74. And we reduce the placing temperature to 26. What will happen to the final temperature? Final temperature will be 68. So by looking at this chart, you can decide what you are going to do. But my advice is, if you are having a large pore, it is because you have not optimized the design. If you have not optimized the design, what are you going to do? Don't use high strength concrete. Well, high strength concrete needs high amount of cement. High amount of cement means we are asking for trouble. So if you are not optimized the structure, you have a large pile cap, use 30 megapascal. Don't use 40. Why? Because pile cap we are not optimized. We are using strut and tie method that I will explain later day. And it is not optimized structure. Why do you want high strength concrete in a structure that is not optimized? So the lesson that you can learn is, don't use high strength concrete just because it is allowed. Because you have to look at the practical aspects, especially with respect to Sri Lanka, where the placing temperatures can be around 30 degrees, 32. And so we are asking for trouble, and people learned it hard way in Southern Highway. We had to do a lot of rectification, and we were directly involved. So after that only we thought, okay, let's help the design engineers by producing a set of charts. But just by looking at this chart, you can decide what to do, how much maximum cement you can use, and whether you have to cool the concrete before placing. Everything is given in one chart. Very valuable information. Is that clear, Bandhuga?
Yes, sir. It's very clear.
Very clear. So this chart is very valuable. I mean, with one chart, you can tell the whole story. But if you look at the paper, we have, produced charts for different amounts of fly ash as well. But it's all additional information. But the most important chart is this one. By looking at this chart, you can, as a design engineer, you can make many important decisions, including the maximum grade of concrete that you are going to use, because now you know how to make the mixed proportion easily. Within few minutes, you can decide, okay, I'm going for 40 megapascal concrete, how much cement I have to use. If I'm using that cement, how to achieve that concrete by cooling the ingredients like aggregates. On the other hand, you decide, okay, I'm going to have a problem when I'm going to construct. So because of that reason, I will settle for 30 megapascal, because anyway, using strut and tie method, I can design with 30 megapascal. So likewise, you have to take important decisions, informed decisions. And so with that, I would like to conclude. Any questions, Manduga, Mangala, or any others?
There were several questions.
Yeah. So I'll stop sharing.
One question I will ask.
I can
One participant has raised. Okay, sir, that's it.
Yeah, what is that? Chat. Where's the chat? Chat. Yes. Chat is empty. Oh no, there are 26.
Yeah, at the end, I think there are a few questions.
Yeah, can you tell the question?
Okay, sir. Okay, I will tell, sir. Sir, this is the question. As you said, sir, C3S has increased compared with past. Will this affect shrinkage properties of the concrete?
No, actually, this is because of the demands of the industry. So what happens is, when you have higher tricalcium silicate content, it will not have a major impact on shrinkage, because what happens is, anyway, when the water is evaporating, concrete will shrink a lot. But when the tricalcium aluminate reaction occurs, tricalcium aluminate has a bigger volume than the original volume. So tricalcium aluminate will give bigger volume. Shrink, concrete is shrinking due to evaporation of water. So it will be compensated in the first 24 hours to a great extent. After that, what you get is a shrinkage, and higher the strength concrete has, lesser the shrinkage. So having tricalcium silicate higher content is not a big problem when it comes to shrinkage.
Okay, sir.
Higher the strength of concrete, lesser the creep, lesser the shrinkage.
Okay, sir.
Okay.
And several have asked these questions. How about controlling the temperature gradient between the core and the surface? I think when gradient between core and the surface.
Talk about it, but I don't really worry about it, because on what basis you are talking about the core temperature and but most important thing is reduce the core temperature, right? Because the control the temperature gradient is a big topic, but we have very little control of it. So what you have to do is, if you are worried about it, add 8 millimeter bars, extra bars between your main bars, because lesser the space, lesser the crack width. So this concrete gradient is something that we cannot control easily, but it's far easier to control the core temperature, right? Because you do a big concrete, right? And that night we have a big downpour. The temperature in our, so when there's a heavy rain, temperature can drop to 25 easily. Now, outside temperature drop suddenly. I mean, how are you going to control it? No way. So if you are worried about it, add an additional 8 millimeter layer on the surface, right? And all these 8 millimeter bars will reduce the bar spacing to a great extent the moment bar spacing is controlled, and we have extra reinforcement on it, and nothing will happen to the concrete. Okay.
Okay, sir. So basically, sir is suggesting to address
this concrete gradient is something that we are talking where we have no way of controlling. So in engineering, we must always talk about things that we have control. Otherwise, we must come up with alternative ways of controlling the impact. So the alternative way of controlling the impact is actually adding some extra 8 millimeter bars, because they are for per ton we get 440 bars, so we can easily add 8 millimeter bars in between the main bars. The moment the bar spacing is reduced, there's no way the concrete can crack. Right? Is that clear?
Okay. Yeah, that's
right? So the most important thing is reducing the maximum core temperature.
That means we have to address that issue in the mix design
core
stage.
temperature problem is addressed by adding fly ash and keeping the cement content low.
Okay, sir. Clear, sir.
Right. Any other question?
I think one has asked, sir, according to the Eurocode, can you clarify how concrete exposure
Yeah, so I'm going to do it
establish the minimum cover value?
How to find the cover condition, how to find the cover for a concrete, I'll cover next time.
Okay, that's fine, sir.
Next week, right? Okay.
So I have one more question on this strength. You said we are replacing the cement content with fly ash. How it is going to impact the strength?
No, actually, it's not going to impact the strength. You will get the same strength over a longer period of time. So instead of getting 28 days strength in 7 days, you will get the 28 days strength in 20 days. That's the only thing.
Okay, let's say we are going to we are dealing with the construction of a typical floor construction. So let's say we need to remove the formwork within 3 days or within 5 days. So in that case, what is your opinion on this fly ash concrete?
In that case, because you are talking about a normal concrete where the thickness is 300 less than 300 millimeters, there is no way you can get DF in that. Because if you look at the chart, you can see when the thickness is 300 millimeters. You can see when the thickness is 300 millimeters, right? Whatever, I mean, even if you are using 350, this 275, 300, 350, 375. Even when you are using 375 cement, still the temperature is less than 70, so you have no problem. So don't use fly ash. In that case, use cement and do the concrete. So you get high strength, very high strength gain over a very short period, and you can remove the sharpness.
Thank you. Thank you. Yeah, thank you. Thank you very much.
Any other question, Manduka?
I think that's all.
That's all. So we'll wind up today, and we'll continue from next week onwards. 6th I can take the lecture.
I will put some questions, some of these questions in the group chat, sir. There are many questions coming.
Oh, yeah. Yes, please. Then I also can make contribution once in a while.
Yes, sir. And also we are going to add these new members to this our WhatsApp group as well. So that
I will share the link again.
Yeah. So I hope Bandhuka, you are going to do
a lot of engineers are asking for the link.
Yeah. I will share it again, sir.
Yeah. You better. Yes.
And
1 minute.
Bandhuka, I think Professor Bandhuka will do the formal vote of thanks on this first day. Right? Bandhuka, please do it.
Yeah. Okay. Actually, we are grateful to Professor Tisan Jayasinghe, because actually when he was the chairman in Civil Engineering Sectional Committee 2 years back, he himself started this lecture series starting from tall buildings, and then continued the lecture series of structural design of highway bridges under the chairmanship of engineer Mrs. Kamala Gunawardena last year. And this year also, the Civil Engineering Sectional Committee Chairman, Engineer Mangala Silva, Professor, is continuing this lecture series. Actually, these lecture series have make a trend in the sectional committees and as well as IESL, because most of the participants are engaging with our activities because of conducting this lecture series. So we are very thankful for Professor Tisan Jayasinghe for setting up this trend, and also this is a great service for the engineering community of Sri Lanka as well, because this is uplifting the knowledge of local engineers. That is a very valuable thing. So thanks again, Professor Tisan Jayasinghe, sir, for your valuable commitment.
Okay, thank you,
contribution for this. And also for the participants, I will wait for a while. I couldn't find the link again. I will share in 2 minutes and again the link for the WhatsApp group. In that group, actually, we will share the study materials, all the study materials, lecture series, and also the recordings. We are publishing these recordings in IESL YouTube channel, IESL Media, and also in Civil Engineering Sectional Committee channels. So we will share those details with you. Thank you very much, everyone. And Engineer Mangala Silva, do you have anything to add?
No, actually, I have to say thank you very much to our Professor Jayasinghe. Thank you very much, sir. Actually, you are a great, great strength to our sectional committee. Thank you very much.
Thank you.
Good night.
Hey, good night.
Okay. Good night, everyone. For those who are waiting for the link, wait for a while. I will put it in the chat.